I think we are now all set for the first talk of this session, which will be given by Professor Sourav Chatterjee from the Mathematics and Statistics Department of the Stanford University, and he will speak to us on a definition of spectral gap for non-reversible Markov chains. Over to Professor Chatterjee.
Okay, thank you very much for the introduction and for the invitation. It's a great pleasure and honor to be here at this conference. And so I understand that there are it's a mixed audience. So I decided to speak on something which only involves some very elementary math and a probability, sort of an undergraduate background in probability. That should be fine. Or just quarter random variables, Markov chains. That should be fine. Let's see. Okay. So let x0, x1, x2, etc. be a time homogeneous stationary Markov chain on a finite state space. Okay. And let P be the transition matrix of the chain. And let mu be an invariant probability measure for the chain, so that it puts positive mass on every point. So that if you start, the initial random variable is drawn from that probability measure. It keeps being having the same distribution. And then this measure defines an inner product in the usual way. So the inner product of two functions f and g on this state space is a summation of fx conjugate of gx times mu x. And the Markov chain is said to be reversible if this transition matrix P, considered as a linear operator on the space, is self-adjoint with respect to this inner product. And that's a definition of reversibility. And if the chain is reversible, then it can be shown using the fact that it's a Markov chain, that it has this transition matrix has real eigenvalues, which are bounded between 1 and -1. The largest eigenvalue is always 1. And then you have these other eigenvalues, and these are repeated by multiplicities. So S is the state space. So as many eigenvalues as there are points in the state space, we are only considering finite state spaces. The spectral gap of the chain is defined as 1 minus the second largest eigenvalue. Okay. And the absolute spectral gap is 1 minus the maximum of the second largest and the absolute value of the smallest. So it can happen that the smallest is much closer to -1 than the second largest is close to 1. So we take that into account. And there is a certain condition, you can easily make it that all eigenvalues are non-negative. So if you just hold the chain, so what you do is you have this Markov chain jumping around from state to state, and you just decree that wherever it is with probability at least a half, it will just stay there before taking the next step. So that means to replace the transition matrix by the average of the transition matrix at the identity. If you do that, then you have a holding probability that it just stays where it is with probability at least a half. Sometimes this is called strongly aperiodic. And any chain can be made strongly aperiodic by decreeing that at each step, it just stays where it is with probability a half. And for strongly aperiodic chains, all the eigenvalues are non-negative. That's easy to show because the initial chain, all the eigenvalues are between 1 and -1. And in that case, the spectral gap is just the absolute spectral gap. And the relaxation time of the chain is defined with the reciprocal of the absolute spectral gap. So, we'll just assume that the absolute spectral gap and the spectral gap are the same. And then under that, the relaxation time is just 1 over the spectral gap. Okay. So, any questions so far? Okay. So these are just all very basic definitions. And so what is the relaxation time? I said it's a certain kind of time. So what happens at that time? For reversible chains, the relaxation time can be characterized as the time required for decorrelation of L2 functions. So more explicitly, if you have a reversible Markov chain, and you have two functions f and g, L2 functions, then the correlation between fx0 and gxn is bounded by 1 minus 1 over the relaxation time to the power n. And equality is attained if we take f equals g to be the eigenvector corresponding to the second largest eigenvalue. And so this tells you that if you want, so the correlation is the usual correlation. So I'm not writing down the definition, but it's just the covariance of two random variables divided by the product of the standard deviations. So the usual Pearson correlation. And so this shows that the relaxation time is exactly the time it takes to decorrelate between functions at the initial time and functions at time n. So if n is much bigger than the relaxation time, then this inequality shows that you have approximate decorrelate random variables. And they have many other important properties, the spectral gap and the relaxation time, and they are central to the analysis of reversible Markov chains. Okay. So now, so there have been many attempts at defining spectral gap for non-reversible chains, but none that is very widely accepted. And I'll give you the reasons why, what goes wrong. So, and first of all, if you don't have self-adjoint, you don't have these real eigenvalues. So first, that's the first hurdle. And then maybe you can think of using some other property. So what would be a right definition? And there have been, as you can expect, many attempts. So for example, one popular definition of spectral gap for non-reversible chains is 1 minus the second largest singular value of the matrix P. So the eigenvalues are no longer real, but the singular values are always real. So just to refresh your linear algebra, the singular values are the square roots of the eigenvalues of P star P. Okay, so that's those are all real and non-negative. And sometimes this is taken to the definition. So if gamma denotes this spectral gap, then the chain has a contraction property that if you take any function f with mean of f equals 0 with respect to the stationary measure, then the L2 norm of pf is contracts by 1 minus gamma of the L2 norm of f. So there's a contraction, and that ensures that the chain converges geometrically to the limit. However, if one defines the relaxation time to be the inverse of this spectral gap, it may lead to misleading pictures. So that's very interesting. So I'll show you the striking example in the next slide. Why this contraction doesn't really tell you the real rate of convergence. Okay. So here's an example. The Chang diagonal Graham chain is a very simple Markov chain on Z mod NZ, which just goes as follows. So if you are xi at time I, xi plus 1 is you just take 2 times xi, and then you take a little random error. So epsilon I plus 1 is either 0, 1, or minus 1 with equal probability. So it's just like, in ergodic theory, you take the map 2 times x mod n, but here you are doing a little perturbation of that. And then you ask, how fast does this get close to uniform? So the second largest singular value of the transition matrix you can calculate, I'll not show you the calculation. It's like 1 minus constant over n squared. And therefore, the relaxation time is of order n squared, just like as if you were doing simple random walk, plus minus 1. It takes n squared time to mix. So if you look at the same largest singular value of p, it gives you the same answer. That is, it will tell you it takes at most n squared time to mix. However, this is much faster. So one can show that the mixing time is at most of order log n times log n, and that's attained. So I'll tell you about that later on. It's log n log n, and so it mixes much faster than simple random walk. So here you see you're doing simple random walk and alternating with a doubling. So you take doubling and simple, and it becomes close to uniform very, very quickly. Okay. So if you look at the spectral gap, if we define the relaxation time to be 1 minus the second largest singular value, it gives you a completely wrong answer, even in this extremely simple and natural example. Okay. So I just talked about one definition that people use. There are other definitions that people use, but surprisingly, no one has used this. So given a Markov chain of finite state space with transition matrix P, I define the spectral gap to the second smallest singular value of I minus P. And note very quickly that unless the change is reversible, there is no obvious relation between this and the spectral gap mentioned earlier. So what I mentioned earlier is the second largest singular value of P, and then you take 1 minus that. Here I'm just saying the second smallest singular value of I minus, and there is no connection between the two numbers unless P is self-adjoint. Okay, and I define the relaxation time to be the reciprocal of the spectral gap, and henceforth I'll denote it by tau, and I'll show that it has many nice properties, and it sort of is, I would claim it's the right thing to look at. Okay, so let me state the main result. Suppose you choose a starting state which comes from the stationary distribution. You start from stationarity, and you look at the empirical average of some function g. So you look at the time average. So you take some function g, you look at summation g xi I from 0 to n minus 1 divided by n, look at how close it is to the limit mu g, and take the expected square of that and to the power half, so the L2 norm. And you take supreme over class functions, you take over all g, so that g minus mu g has norm 1, so call that delta n. So delta n is a rate at which these averages, time averages, are converging to the limit. So it's a measure of that, how fast the time average. So the main theorem, which I will explain in the next slide, shows that this delta n is small if and only if n is much bigger than this relaxation time that I defined. Okay. So that's an if and only if condition. And so this gives the characterization of this relaxation time as the convergence of time averages to their limiting values in L2. So here's the theorem. So for any n, delta n is less than or equal to square root of 4 tau over n, where tau is the relaxation time that we defined. And if n is less than tau over 3, delta n is bigger than 1 over 132. Okay. So this is in complete generality overall Markov chains, including discrete dynamical systems. Any questions about this?
At the outset, you said something about you are going to assume without loss of them that absolute spectral gap equals spectral.
No, I'm not assuming here. No, there is no assumption. Yeah, there is no hidden assumption in this. This is just any finite state space, and I suspect there is nothing in this result that requires a finite state space. So I have to look into that. But if you consider infinite state spaces, obviously issues of measurability, etc., will come up. So I haven't worked those things out. So one immediate remark is that contraction is not necessary. Consider the Markov chain on Z mod nz, which always moves one step to the right. So xi plus 1 is xi plus 1 mod n. So you always move one step to the right along a circle. Okay, so it's a very simple dynamical system. This chain never mixes. In particular, P is not contracting and correlations don't tend to 0. So correlation between any function of x0 and any function of xn, does not tend to 0 as n tends to infinity. However, if you think about it a little, you see that this empirical averages, the time averages, should converge in time n because you are going round and round over the same space. So if you take the averages, it will take time n to converge. And indeed, you can show that the second smallest singular value of this transition matrix is of order 1 over n. So that you don't need contraction. So for this Chung diagonist Graham chain, I could prove that this relaxation time that I defined is of order log n up to constants, whenever n is a prime. Okay. And therefore, the empirical averages converge at time log n, whenever n is a prime. The mixing time of the chain, if n is a Mersenne prime, it is known that it's exactly of order log n log n, so it's a little bit bigger than that. And I'll talk about some more examples later on. Okay, so this is just okay. So I'll show you some math, but it will be very simple, simple math. So how do you prove this result? So there are two parts. upper bound and lower bound. Okay, and I can present both parts within this talk. Okay, so let's prove the upper bound. Take any G on the state space which has mean 0 with respect to the stationary measure and has L to norm equals 1, again, with respect to the inner product defined by the stationary measure. So then, if you take the chain xi, if you take expectation of gxi, gxj, it becomes the inner product of g and p to the j minus I g. So p is this operator defined by the transition matrix of the chain. So if you take I less than or equal to j, then you have this identity. So then, if you take the expected value of the squared, which is our main object of interest, you expand it out, and then you can write it as follows: 2 over n squared, the upper bound is 2 over n squared summation I equals to n minus 1, g inner product of g and h n minus I, where h is this new sequence of functions. Hk is a summation of p to the mg, m from 0 to k minus 1. Okay. So you can write it, it's just expanding out the square, and then applying this fact that the expectation of gxi, gxj is this inner product g p to the j minus I times g. And then by Cauchy-Schwarz, you get this inequality because norm of g is 1. So you end up with this upper bound, that the expected value of the empirical average square. So here, I've assumed that mu g is 0. So we are trying to understand the rate at which these averages converge to 0. So expected value squared is bounded by 2 over n squared times the sum of these norms of hk, where hk are these partial sums, p to the mg. So now, what you do is you try to solve LF equals G, where L is this generator, I minus P. And, so by the definition of tau, since 1 over tau is the second smallest singular value of L, you have this inequality that the norm of G is 1, which is norm of LF, but it's at least 1 over tau times F, because G is orthogonal to the constant vector. So therefore, the second smallest singular value can be used to get this lower bound, which means the norm of F is bounded by tau. And this h of k, it simplifies. So hk, remember, is p to the m g summed from m equals 0 to k minus 1. But g is I minus p times f. Okay, so it becomes a telescoping sum. So you have this telescoping thing. And you just get this, that hk norm is bounded by 2 times tau. This is uniform bound over all k. Okay, so you remember you had this bound in the previous slide that the empirical average squared expectation is 2 over n squared sum of these hk norms. And these hk's are summed from 0 to k minus 1 of p to the mg. And then I use this trick to show that this hk, the norm of hk is bounded by 2 tau irrespective of k. Okay, so this is the main equality, and what this trick allows is to replace contraction by cancellation. So if you have a contracting semigroup, then you have p to the m times f contracts. Here you don't have that. For example, in the example where the point moves around the circle, you don't have that. However, if you take the summation p to the m times g and sum over k, there is some cancellation that's coming up, which ensures that for any k you get a uniform bound, even though p to the m times g is not converging to 0. Okay, even though it's not converging to 0, cancellation, there is some kind of cancellation that goes on which ensures this. And then you have this bound. So the expectation squared, you get this, you plug in this upper bound on hk, and you get 4 tau over n. And if n is bigger than tau, this shows that the thing has converged. Okay, so that's the upper bound, a very simple proof. Okay, and as you can see, I used Markov chains very minimally here. Okay, any questions about this? Yes. No, I didn't assume irreducibility. However, the second smallest eigenvalue will be 0 unless it's irreducible. So the relaxation time will be infinity unless it's irreducible. So there's So that's inbuilt into this. So if you look in the actual paper, I have two sections. What if tau equals infinity? Then there is a proof which is very simple, and then if tau is finite. So tau finite automatically tells you that it's irreducible. Other questions? Yes, there are lots of things. I'll come to that. So you can have Cheeger inequalities for this thing. Okay. So the lower bound, again, this is a little bit of math here. So what I want to show is that if tau is less than n is less than tau over 3, you have the number of steps is less than 1/3 of this flexion time, then this delta n is at least 1 over 132. This general lower bound. So what you do is you start with any f that minimizes this norm of LF subject to these constraints, and you take G equals LF. So note that with this minimization, the norm of G is gamma and mu G is 0. So gamma is the second smallest singular value, and then it's a I don't know. This just works. So there is no particular intuition behind this. So what you do is you decompose your f to two parts: f minus the average of p to the k f from n to n minus 1, and vn to be this other part, so that f is un plus vn. So you know that the norm un plus norm vn is at least 1, because norm f is 1. And then you recall that h delta n is this supremum. So what you do is this un, you can write it as this telescoping average, and you come back to this average of hkk from n to 2n minus 1. Okay. And sorry, I'll just go over this quickly. So what you have is that hk you can again bound using delta k. So what you end up with is so let me skip over these things. So what you end up with is that this inequality that for any n, you have this lower bound that 1 is less than or equal to 2n gamma plus 3 times the maximum of this delta k between n and 2n. Okay? And what this tells you is that if n is less than 4 tau, for instance, then if you plug in n is less than 4 tau, where tau is 1 over gamma, you get this maximum times 11 is bigger than 1, so this maximum is bigger than 1 over 11. And from there you can, with this a kind of subadditive inequality, you can deduce that if n is less than tau over 3, then there is some then delta n is at least 1 over 132. So it doesn't mix. But yeah, I'll not go over the details of this. But if you're interested, you can ask me for the details of this proof. Okay, so it gives this upper and lower bound. It shows that if the time n is less than this relaxation time that we defined, then the time averages are not converging, and if it's bigger, then the time averages are converging. Okay, so let's see an example. Another example. So Chatterjee is branch chain is 1. So take any dimension, let pi, I between minus d and d be a set of non-negative real numbers of sum to 1, and consider the random walk on z mod nz to the power d, which takes independent steps as it stays where it is with probability p0 and goes to one of its neighbors with probability is pi. So it goes up towards xn is xn minus 1 plus ei with probability pi, and minus ei with probability p minus I. So it's a general form for Markov chain which just goes to one of the neighbors from each point. And then we assume that pi plus p minus I is positive for each I, otherwise the Markov chain is not irreducible. So otherwise there is some direction in which it's never moving. Okay. So under this condition, the uniform distribution on the torus is the unique invariant measure of this law. It's not hard to show that the mixing time of this chain is of order n squared for any choice of pi's. For any choice of pi satisfying this constraint. So mixing time, I'll tell you more about mixing time later on, but it's a time that it takes for the chain to get random. Okay. So that is of order n squared. So there's nothing very interesting going on there. However, the time for averages to converge behaves quite differently. So the relaxation time, according to our definition of this random walk, is at most of order n squared. You can prove that for any PIs and any dimension. However, if dimension is 1, then this is of order n squared if the chain is reversible, and of order n if it is not. So there is a reduction. So even though it always takes times n squared to mix, in the sense that to get random, averages converge much faster if you make it non-reversible. Okay. If D is 2 or more, then you can show that if either Pi goes minus P of minus I, so the chance of going up or down in certain direction is the same for some I, or this difference is rational for at least 2 i's, then tau is of at least of order n squared. So this improvement over n squared doesn't happen just by making the chain non-reversible. Okay. Now the question is, can this upper bound be made better than n squared with some choice of Pi's if D is 2 or more? Okay, so that's the question. So, yes.
Significance of rationality.
Yes, I'll come to that in the next slide. Now I can show that for any dimension and any choice of Pi's, tau is at least of order n to the 2D over D plus 1. So there is a uniform lower bound you can prove. The time for averages to converge. And for almost all choices of Pi's with respect to the Lebesgue measure, it actually almost attains this. So tau is n to the 2D over D plus 1 plus little o of 1, but the little o of 1 is an exponent. So you can, with irrational things, you can get close to the optimum. However, you can ask, what about an explicit choice? So I have an example of that also. So for example, if you're considering a two-dimensional torus, and a very simple random walk, which always moves either up or to the right on a two-dimensional torus, but the probability of moving up or right, alpha and 1 minus alpha is an irrational algebraic number of degree 2. Okay. So if that happens, then it is optimal. So then the time for average to converge is n to the 4/3. Okay, so it's upper and lower bounded by some constant times n to the 4/3. Although the chain still mixes in time n squared, averages converge much faster. Okay, so you can attain the optimum using irrational numbers. So I'll sketch the proof of this theorem if I have some time, but let me talk about some of the properties of the chain, including connection to Cheeger constant and so on. But any questions before that?
So this is the Cesaro mixing time, right?
Yeah. Yeah. So this gives an exact characterization of that, the second smallest singular value of the generator. Okay, so here's the connection to Cheeger constant. So if you have a stationary Markov chain with transition matrix P and invariant measure mu, the Cheeger constant is defined as follows. It's the minimum over all subsets of measure at most a half. The chance that you are outside the subset, given that you are initially in the subset in probability language, that's the Cheeger constant of the chain. And a famous property of the Cheeger constant is that if the Markov chain is reversible with spectral gap gamma, then gamma satisfies this upper and lower bound. It's bounded between psi squared over 2 and twice psi. And I don't know if those are the optimal constants. I think those are the optimal constants. So I'm not sure about that. But anyway, so you have these bounds, and it connects the geometry of the Markov chain of the state space with the mixing time of the chain. So here is the analog. Suppose you have any Markov chain, not necessarily reversible. Not the transition matrix is not self-adjoint, and you find the spectral gap to be the second smallest eigenvalue, second smallest singular value of the generator of the chain. Then it satisfies this. The Cheeger constant is defined just as before. The Cheeger constant has nothing to do with the reversibility of the chain. Okay. And it satisfies this upper and lower bound with slightly worse constants. And the proof is different because in the case of reversible chains, we work with eigenvectors, which you cannot do for the non-reversible case. Okay, so there is no other definition of the spectral gap that I know which satisfies this kind of relation with the Cheeger constant. And the proof is quite different, as I said, you cannot work with eigenvectors. There is a relation mixing time. So the mixing time of a Markov chain is defined as follows. So first recall that the variational distance between two probability measures, mu and nu, is defined as the maximum difference between probabilities of sets. So that's the L1 metric. And the mixing time of Markov chain is defined as given some epsilon. So typically epsilon is taken to 1/4 or some constant like that. It's the first time so that there should be a for all x there. So no matter where you start from, the distance between the law of xn at time, the law of the chain at time n, and the target distribution, the total variation distance is less than epsilon. So there's uniform, closeness. And the mixing time and the relaxation time for reversible chains, they satisfy this set of inequalities. And often it's quite suboptimal, but this is the best one can do, is that the mixing time is bounded below by the relaxation time up to a constant, but bounded above by the relaxation times this log of 1 over the minimum probability, and that can mess things up badly. That's the best we have. So the question naturally is whether there is an analog for this new relaxation time that I'm defining. So yes, there is an analog. So again, the mixing time is bounded below by the relaxation time times the constant. But for the upper bound, you need this little, holding. So you need this aperiodicity condition, strongly aperiodic condition that you stay where you are probably at least a half. If you have this, then the mixing time is bounded above by the square of this relaxation times this logarithmic factor. And that's, again, the best you can do. I'll tell you in the next slide. But any questions about this theorem? Okay. So for this second inequality, this condition pxx bigger than or equal to half cannot be dropped. So for example, consider this chain that I talked about already, which is always moving to the right. This never mixes. So you never have that it becomes close to uniformly. You can deterministically predict its position at any point. So the mixing time is infinity, but the relaxation time is finite. So you do need some amount of holding. But as soon as you include this holding, you get a relation between the two things. And also, I have this upper bound. I have the tau squared the upper bound instead of the tau. And this also cannot be improved. So again, for example, you consider this chain, which stays where it is with probability half and moves one step to the right with probability half. And this chain mixes in time squared, but the time for Cesaro averages or time averages or empirical averages to converge is of order n. So you cannot remove that square and make it tau, okay, for non-reversible chains. Then finally, this one slide about if there are some experts in Markov chains in the audience. So there are these reversibilized chains. So recall that P is a transition matrix of Markov chain of finite state space with invariant measure mu. Let P star denote the adjoint of P with respect to the inner product induced by mu. Then the multiplicative reversibilization of this chain is the transition matrix PP star, and the additive reversibilization is the average of P and P star. And these, you can show, these are both Markov chains. They are both Markov transition matrices, and with mu as invariant measure. And these are sometimes used to study non-reversible chains, and you can prove some inequalities. You can show that with the bounds that are attained on both sides. You can show that the spectral gap that we define is bounded below by half of the spectral gap of the additive reversibilization, and bounded above by square root 6 times the spectral gap of the additive reversibilization. And same bounds hold for the multiplicative reversible position also, but with this additional condition that you have some holding. Okay. So there are these relations. However, there is this gap, gamma, and there's gamma on this side and square root on this side. So again, if you use the reversibilized chains to study the rates of convergence, it may lead to a misleading picture up to a square root. Okay. So here's a summary before, so I try to explain this this 1/√2 thing. So I give a definition of spectral gap for general Markov chains in finite state spaces that reduces to the standard definition in the reversible case. And the main result is that this relaxation time, defined to be the inverse of the spectral gap, can be characterized as a time required for these Cesaro averages to converge. And arguably, this is more relevant for practical applications. So when you are doing applications of Markov chains, it's the Cesaro averages or the empirical averages that are more important than mixing time convergence. And then there are these auxiliary results which show that the spectral gap is related to the Chiker constant and the mixing time by inequalities that are similar to the reversible case. And then there are these examples which can show that this can be substantially smaller than the mixing time of the chain if the chain is not reversible. So the time for averages to converge can be much smaller than the time for the chain to mix. And then for the details of the proofs, everything is on this preprint. So before I move on to the example, any questions?
In cases where there are no obvious symmetries present, is there a way of controlling the stationary distribution?
Like
I mean, so you often want these sampling from specific distribution. So in the non-reversible chains, is it always possible to control what the stationary distribution is, or is that
No, so typically Markov chains are constructed to generate from some stationary distribution, and there are all kinds of constructions. And for reversible chains, there are some standard, this Metropolis algorithm. But recently there has been a lot of focus on trying to understand non-reversible chains. So for example, in the hard spheres problem, so you have all these spheres and in the crashing into each other and reflecting. So Werner Kraut has been working on designing non-reversible chains, which makes much faster. And so you can have a lot of situations where making a chain non-reversible can lead to, and it's not always very hard to see that that the stationary distribution is what it should be. So once you're given a candidate stationary distribution, it's usually easy to verify that this is a stationary distribution. But if you're not given a candidate distribution, then in non-reversible, you can make it a bit challenging too. Yeah. Yes. So decorrelation need not happen for non-reversible chains. Yeah, so for example, the chain that I mentioned, which always moves to the right, it never decorrelates. And the chain that stays where it is, with probability half and moves to the right, with probability half. That also doesn't decorrelate by time n. Time takes time n squared to decorrelate. But empirical averages converge much faster than that. And so about this this other thing that why would averages converge faster if you have, let's say, a two-dimensional torus? Okay, so I said n to the 4/3, it takes time n to the 4/3 for averages to converge. So what happens there is that if you, let's say, the chain is only moving up and right. So if you look at it from a distance, it will look like it's going sort of in a straight line. So it's little fluctuations around the straight line. And the straight line will wrap around the torus. And if that angle of the line is irrational, then the straight lines will kind of mix. If it's rational, they will never mix. So the straight lines will mix, but since the chain is random, there will be a fluctuation around the straight line. So the averages will mix as soon as there is some balance that is achieved. So the straight lines have mixed a lot, but then there is some fuzziness around the straight lines which covers the rest. And that's why this n to the 4/3 that comes in. So okay, but anyway, the proof is different. So let me let me show you the proof. So recall this theorem. So let alpha be an irrational algebraic number of degree 2, such as 1/√2. Consider the random walk on the two-dimensional torus, which moves either one step up with probability 1 minus alpha or one step to the right with probability alpha. And the relaxation time of this walk then is of order n to the 4/3. So the time for averages to converge is n to the 4/3. And recall that this relaxation time is inverse of the spectral gap gamma, which is the second smallest singular value of this I minus p. So how do you prove the lower bound? So what you do is let m be a positive integer to be chosen later, and consider these numbers a alpha plus b 1 minus alpha, where a and b range over all integers in minus m to m. So these numbers are all in minus m to m. And there are 2m plus 1 squared choices of a and b, and this minus m to m can be partitioned into 2m squared subintervals of length 1/2m. So therefore, by the pigeonhole principle, you'll be able to find distinct pairs AD and CD, so that both of these are in the same subinterval. And so these are some standard techniques from Diophantine approximation. So you take these differences, so you end up with some k and m, which are integers, not both 0, so that k alpha plus m times 1 minus alpha is less than 1/2m. And then you look at these eigenfunctions of the generator, and what you can then see is that from this inequality, you have that this f of x is fx times 1 plus something small, and then just optimizing over n, taking n to the 1/3, you get I minus pf is n to the minus 4/3. So you can find a function f which is norm 1, but I minus p times f as norm at most n to the minus 4/3. So that gives you one side of the bound, and then for the other side, you can explicitly calculate the singular values of this chain. These are the singular values of this chain. And to show that the smallest singular value is at least n to the minus 4/3 by Taylor approximation, it suffices to show that this quantity that you've done has order n to the minus 4/3. And then again, you apply some techniques from that approximation. So that's why I need a irrational number of degree 2. It solves a quadratic equation with interior coefficients. So you can write it down as follows, where b is not a perfect square, and so let me not go over this too carefully. So since b is not a perfect square, and p and q are integers which are not both 0, we have this is the basic inequality that you apply, that q squared b minus p squared is at least 1, which gives you this lower bound. And then then with this k and m, you apply this lower bound and you get this, sorry, and then just apply Young's inequality, and you end up with showing that for any k and m. So what you need to show is the following: that for any k and m between 0 and n minus 1, which are not both 0, this thing is bounded by n to the 4/3. That's the goal. And for alpha, which is to answer your question, for alpha, which is an irrational number of degree 2, you can show that it's bounded by n to the 4/3, 1 over n to the 4/3. And for a rational number, obviously, you cannot prove that. And so that's the technical part of the argument. So anyhow, so that's the summary, and it seems like that this is the proper notion of spectral gap for a non-reversible chain, which shares all these nice properties the spectral gap has for reversible chains. And so, thank you.
Any more questions over and above what we had in the session?
Yeah.
You have something?
Yeah. So, I mean, reversible Markov, and it's basically this is something following up from Hari's question. So to get this Cheeger inequality, I mean, it's first came for manifold for a continuous setup, and then was discretized. And here you're basically probably having a directed graph.
Yeah.
So is there a geometric interpretation which one can take back to that? I mean,
possibly. So I haven't thought too much. So already, the paper was quite long, so I decided to stop. But possibly, there is nothing that I'm using that's particularly for finite state spaces here. So one can possibly go back to the continuous setting and get something significant maybe.
I don't see any other raised hands, so let us thank the speaker for the next talk.